This is lesson 4 of Unit 12. In this lesson we'll talk about phase changes and the accompanying energy changes. So we know that to go from a solid to a liquid, this is called melting. We know from a liquid to a gas, this is called vaporization. Now remember, this is different than evaporation. We distinguish between the two. Evaporation happens at any temperature, room temperature. Vaporization has to happen at the boiling point. And then we can also go from a solid to a gas. Remember, this was called sublimation. Now in each one of these cases, what happens is the molecules have to speed up. Remember, for example, in a liquid, the particles are close together, they touch one another, they can slide past each other. But in a gas, the particles are all over the place, and they have much more energy. So in order to go from a liquid to a gas, the molecules must have absorbed energy. They must have taken energy in from the outside. So this phase change is called endothermic. Endothermic means heat is absorbed into the system, by the system. This is why the gas particles move faster than the liquid particles, and the liquid particles move faster than the solid particles. Remember, solid particles are pretty set. All they do is they vibrate. So anytime you go from a solid to a liquid to a gas, this is always an endothermic process. This is an important term, vocab term, meaning into. Heat, thermic means heat, endo means into. Heat is going into the system. And each time you are breaking the intermolecular bonds. So intermolecular bonds are broken between the liquid particles when you become a gas. So this is always, and same thing if you just heat up a liquid. This makes sense. If you want to heat up a liquid, you have to put energy into it. Well, if you want to make it into a gas, energy must be put into it. Now there's a special graph that actually summarizes the whole process. It's called the heating curve, and the heating curve can be constructed for any substance. We'll say this is the heating curve for water. And what will happen is we will plot on the x-axis time, or sometimes progress. Sometimes it'll just say progress. Sometimes it can actually say heat. That's also a possibility. And on the y-axis we plot temperature. Now what you'll see is every heating curve has 5 parts to it. 1, 2, 3, 4, 5. And these correspond to the 5 events. Now the 2 flat lines are melting and boiling. Now we know that water melts at 0 degrees Celsius, and water boils at 100 degrees Celsius. This is a little tight, but we'll say that's 100. And what happens, if we begin here, we'll begin at some cold temperature, -15. So here we begin with ice. Now we're going to take ice, and we're going to heat it up. We're going to add energy into it, put heat into it, and the temperature will go up. Now the temperature will go up until you get to 0, the melting point of water, and then temperature will stop going up. As the water melts, or as the ice melts into water, the temperature does not change because all the energy is going into breaking the bonds. We are breaking intermolecular bonds here. That's why temperature is steady. This is actually very important. Then, after we melted all the ice, now we have to heat up the liquid to 100 degrees Celsius, to the boiling point, and then there's another flat line where the bonds again are breaking. And here we're breaking them completely. Here we're loosening them up. In fact, what you always see is that the first flat line, the melting flat line, is shorter than the boiling flat line. And usually it's even more pronounced than this. Usually it's more like this. The second line is much longer because it takes much more heat to completely break the bonds. Remember here, what we're doing is we're completely breaking the bonds. Completely. There are no more bonds after we're done with it. Here, we're simply loosening the bonds. So here we're going from a solid, say, to a liquid, which the molecules are a little loosened up, but the change isn't that drastic, is the idea. And then after we boiled all of it, then we would heat the gas. In this region, we're heating the gas, energy is going in. So what you'll see is that in each case, the temperature changes if you are heating up the solid, as in the case here, if you're heating up the liquid, and if you're heating up the gas, the temperature is changing. But during the phase changes, the temperature stays the same. In fact, you can demonstrate this yourself if you try it, and in fact we will try it. If you take yourself a beaker of water, and bring it to boiling and stick a thermometer in there, and as the beaker of water is boiling, the temperature on the thermometer will stay the same. It will not go up, even though there's more heat put into the system. The temperature on the thermometer will remain the same. Okay? So let's talk about the same thing, but going backwards. And this is going from a gas to a liquid. This, remember, is called condensation. From a liquid to a solid was called freezing. These terms are from first semester. From gas to a solid, remember, it's called deposition. Like depositing, deposition. Now, each one of these, the particles must slow down. So again, if you think about a liquid, liquid particles are kind of moving around, touching each other, and gas particles are not attracted to each other at all. They just go around very fast, moving around very quickly. In order for gas particles to come together and stop moving or start moving slowing down, they must get rid of the energy they have here in the gas phase. So when they give up energy, this is called exothermic. An exothermic process. Heat is released by the system. So anytime you cool something down, heat must be released. The system must give up the heat. Same thing if you go from liquid to a solid, the particles have to slow down, and now they're attached to each other firmly, is the idea. Now, this is because intermolecular bonds are formed. So anytime you form bonds, energy is released. Energy is released. This is always the case. This is actually the case if you form physical or chemical bonds. In this chapter, we're talking about physical bonds. But if you were talking about chemical bonds, the same thing would happen. Let's take a look at a graph that does the same thing for the cooling curve. So here's you could say the cooling curve for water. We can say the same thing. And again, the cooling curve can be applied to any substance. The only difference would be this temperature and this temperature. It won't be 100 and 0. If you have another chemical, it may be 380 or something like that. So we begin with a gas. So in this case, it would be water vapor. The term for water gas is water vapor. And then we're going to cool the water vapor until it gets to 100 degrees. Say we'll begin at 250 degrees or something, very nice and warm, very hot. And then we get to a flat portion. This is the condensation portion, the phase change again. And the temperature will not go down. The temperature, notice, is staying steady. That's because the energy is actually being released, and the temperature essentially is not changing. It's a phase change. And then after you completely condensed all the gaseous water, then you would cool the water. Then you would again come to the freezing of water, and then you got ice water. So this would be ice in our case. Now, what you see is something called supercooling. We actually will show you, demonstrate this phenomenon to you, supercooling, in class. It's a little trick you can do. You can actually go below the freezing point for just a little bit as we supercool. So, same idea, only backwards. Very important to understand that during the phase changes, there is no temperature change. So, no temp change. And same thing here, no temp change. Okay? So the next idea or two we'll discuss are, we should say this, this is liquefaction. Now this is a new phase change that we haven't heard before, and this is a gas going to a liquid, but this is different than condensation. Condensation is usually by cooling, but this is by compression. This is done through compression. In fact, anytime you can actually buy cylinders, or you can see these cylinders in hospitals, of oxygen gas, or cylinders of oxygen. But if you listen around, if you take a look, the oxygen is actually a liquid. It's not a gas, it's actually a liquid. And to be truthful, it's actually like a liquid gas. It's kind of a strange idea we'll talk about in the next lesson. And the way they got the oxygen to be liquid, remember oxygen is a gas in the air, the way they got it to be a liquid is by compressing it. So when you compress the particles, here if you have a gas, if you want to make the gas into a liquid, you can either cool the gas and the molecules slow down, and then condense to each other, or you can compress the gas. You can actually put the gas particles very, very close together. You can force them really, really close together. This has to happen at a pretty high temperature, or I'm sorry, pretty high pressure, And usually you have to try to remove the heat, because remember, if you increase the pressure, the temperature increases. Then you have to remove that heat. And then if you force them close enough, the attractive forces between them will come into play. We'll force them together, and it will liquefy. Now you have to keep them under a very high pressure in order for them to remain a liquid. And this is essentially what happens with gases. This is how they make liquids out of a gas. Very commonly you can also get nitrogen. You may have heard of liquid nitrogen. Liquid nitrogen. Okay, and here's a picture of the idea of liquefaction. These huge pressure towers. This is actually something that's related to it. This is actually distillation. This is called distillation. Okay. By the way, this is also an exothermic process because bonds are formed. So this is very similar to condensation, except it's done through compression. All right. So let's go ahead and do an example problem, and we'll finish the lesson. The example problem says, tell whether heat is absorbed or released by the molecules during the following phase changes. Ice cubes form in the freezer. Now this is strange because you think the freezer is very cold, and it is cold, but when water goes from a liquid to a solid, and here you have your ice cube, maybe a little bit still left. This process, the particles have to slow down or speed up. Well, the particles have to slow down. In order for them to slow down, they must release energy. Must release. This is very strange, but true. Whenever a liquid becomes a solid, whenever ice freezes, it releases heat. And this is tough to believe because we know ice is cold. It does release heat. In fact, farmers use this trick in warm climates. Whenever, say, if they're growing oranges, if farmers are growing oranges, here's an orange, and leaf for it. If they know that it's going to get very cold at night, what they'll do is they'll actually spray their oranges. So here's a hose. Spray their oranges with water overnight, and what will happen? They're trees with water. The water, as it freezes, so then you get an orange afterwards. That still an orange, but it has a bunch of frozen water on it. It's got like an icicle, a few icicles like this on it. As it freezes overnight, it releases some heat to the orange, keeping it warm, keeping it from frostbite, or keeping it from becoming damaged, essentially. And then when it warms back up again in the daytime, the oranges are fine. So this is actually used in the real world. And the second example is butane. Liquid butane becomes gas as it leaves the lighter. Now if you ever take a look at a butane lighter, your regular lighters, I don't know what they look like, but it's probably like a little roll. And the butane, if you ever look, some of them are see-through, you see that it's a liquid. But if you were to push the button, if you push down on the button, then you hear a gas coming out. And this is because butane is actually a gas at regular conditions. So whenever it becomes a liquid, whenever it goes from a liquid to a gas, the particles must speed up. Because the particles are speeding up, they must absorb energy. Absorb energy in order for them to speed up. And this is also, you can say, why a pressurized can feels colder, because energy has to go in to spread the molecules out. That's another explanation of it. All right, try an example problem of your own, and also try not only to get the right answer, but try to justify it with an explanation. So this completes for us lesson 4 of Unit 12.